This is major in 2023, paper 1-2 of O-levels. Question number 1 says, in this experiment, it's a rolled curve track. Which instrument can help you to measure this? So since it's a curved shape, we can't use an instrument that is rigid in its construction, at least, because we want to make sure that it actually moves along this curved path, or you can say at least sticks to the curved surface. So meter rule, micrometer and stopwatch, not entirely completely. So tape measure would be the best option, would be the best choice of equipment to move forward. Question number 2 says, we have to figure out which is vector and which is scalar. So we can very simply see acceleration is a vector quantity, displacement is vector, distance is scalar, speed is scalar. So option D seems to get this right. Okay, question number 3, a very simple, straightforward question. He says, what size in the resultant force of these two forces? So we can use any of the methods that I've explained in the previous videos of vector addition. You can use head to tail, you can use parallelogram method, you can use arcing method, but a very simple common technique would be to just replace this vector over here by the head to tail method. And then you can very clearly see that this is going to be solved very easily by using the Pythagoras theorem. So this is 4, this is 3 newtons as it is. This is your resultant. We can calculate the 3 square plus 4 square with the under root. So the resultant of this question is going to come out as 5 newtons. Make sure that you solve this correctly on the calculators. Question number 4 is a curved line or distance time graph. There is a straight line tangent to the curve at 10 seconds. Tangents are usually drawn to find out the gradient. Now, before starting the question, let's see what the gradient represents. So gradient is change in y divided by change in x. What's on the y-axis? It's distance. The unit is meters. What's on the x-axis? It's time. So that is seconds. So this is meters per second, which is going to represent speed. This is a preemptive assumption before moving to the question. What is the speed of the object at 10 seconds? So you can't choose. This is a mistake that students do. You can't choose these values from the graph by simply using the formula speed equals to distance over time. That is the first mistake and the most common mistake that I've seen students do. You have to go towards the gradient. You can't avoid it. Now, luckily for us, what he has done, he has given us this straight line. We can pick out the values from the graph very easily. We can see that at this point, we have a coordinate of 3 and this is 0. So this is 0, 3 in the formation of x, y. Let's find out the gradient at the second half of the equation or the system so that we can figure out. Let's zoom into this and see if we can find out another coordinate. All right, so I can see that there is one coordinate over here that goes to 9, right? And this goes to approximately, let's zoom out and see where it goes. So it goes to 20. So this is going to be 20, 9. Then we simply have to put in the values of the gradient. So this is x, y. So change in y divided by change in x. So that will be 9 minus 3 divided by 20 minus 0, which if you use a calculator, it's going to be 6 divided by 20. This comes out as 0.3. And 0.3 is option A. So question number 4 is option A. And question 5 says, which of these equipments can measure the mass correctly, even if you take it to another planet? Now, this is partly a part of your memory and partly in terms of discussion. So we understand that the first equipment is spring balance, and it experiences a force because of the weight, which is mg, and applies a counterintuitive force in terms of kx, which is going to come from Hooke's law. So the kx factor is actually being equated to the gravitational factor. So the first equipment cannot eliminate the factor of changing gravitational field if you change the planet entirely. Top and balance is electronic balance, and they are also calibrated for a specific area, for a specific value of acceleration of g. Now, there is a load cell, or you can say there is a constraint or an object inside this, which actually tells you how much force laterally has been applied on that object. Now, of course, if you change the planet, how much force you apply as mg on this object is going to change because value of g is changing. So again, this equipment depends on the value of g. But if you move towards y, we can see that if we want to measure mass, this is employing the principle of moment. So this is going to become mg as the force multiplied by its perpendicular distance up to the pivot. So this is going to become mgd being equated to the anti-clockwise moment, which is going to be for the second mass. Let's say this is m2. So m2g multiplied by whatever the distance on the meter rule is being measured or is being tallied. So this is going to be m1gd multiplied by m2gd2, let's say. Now we can see that in this application, the value of g is going to get cancelled out from both sides, which means that equipment Y eliminates the effect of gravitational acceleration. So even if you take it to the Earth, if you take it to the Moon, you take it to any other planet, it will not care about the value of g. So because it is comparing m1 and d and m2 and d. The same thing happens with this top band balance as well. What we do is we deliberately calibrate, or you can say construct this in such a way that the distance d1 and distance d2 are actually equal to each other. So at the end of the day, what actually happens is that, let's say this is m1g and this anti-clockwise is m2g. When you apply the principle of moment and you put in the values of the distance in this, under a balance condition, of course, we can see very clearly that the value of g gets cancelled out because you're still standing on the same planet. The value of d cancels out because you deliberately made them equal during manufacturing process. So at the end of the day, it is only comparing m2 with m1. So only masses are being compared. So the best equipment to measure mass, irrespective of the planet, is z and y, right? So y and z are going to be part of question 5, part D. Question 6 again, it employs mass weight density. He says that the gravitational field strength is 3.7, the weight is 370. So let's find out the value of mass. So W equals to mg. 370 is the weight, mass is we don't know, g is 3.7, m comes out as 100 kilograms. So this means that option C and D are going to get cancelled out. We're not going to even look at them, no need to think about them. Let's move on to the weight. So when you move to Earth, you use W equals to mg again. Mass does not change, we understand that, and the value of g on Earth is 9.8. So this is going to come out as 980 newtons. Although, of course, we could have quickly seen that this is going to be the answer, but for those who are unable to understand this, I've solved this as well. Question number 7 says that want to determine the density. Now first write down the formula for density. That will be mass divided by volume. So we need something that can measure mass and we need something that can measure volume. So we have a balance and a ruler. Now balance does give me mass, but ruler does not help me to do anything. A balance gives me mass, measuring cylinder gives me volume. So most likely the answer should be B, but let's move on with the rest of the options just to eliminate any thoughts. So beaker needed for volume. Yes, measuring cylinder also tells me volume. So I have two equipments that do the same job. So again, this option is incorrect. A ruler does not do anything. Beaker measures volume. So the correct answer will be option B. Question number 8, Newton's third law describes. Now we understand that we memorize this equation by action and reaction are equal and opposite. But what are the nature of the forces? Are they supposed to be different or are they supposed to be same? This is one of the misconceptions. So as a part of the definition, the nature of the forces should be same. The second thing, that the object that they act on are supposed to be different. They're not acting on the same object. Because if you look at some other resources, he says that there is a force between them. So force FA, or you can say FB, is acting on A because of B. And a force FA is acting on the object B because of A. So the nature of the force is going to be same. Their values are equal and opposite, yes, but they are going to be acting on different objects. A very classic example of this is with the book and the table. I would likely recommend you to go and watch the video of Newton's third law from the channel to fully understand this example as well and misconceptions associated with it. Question number 9 says, now he's going to confuse you in the words from this question. He says, he tells you himself, this is the definition of the stopping distance, is written in the book as well. That is the thinking distance, let me call this as TD, and braking distance, let me call this as BD, and stopping distance, let's call this SD. So he says stopping distance is actually equal to the thinking distance plus the braking distance. Now, let's discuss what is thinking. So thinking distance is purely going to depend on the driver. Is the driver alert? Is the driver under the influence of any drugs? Or is he paying attention to the road? Is he using a phone while driving? And braking distance is primarily dependent on the environment or your vehicle or the condition of the road. So it depends on the car, depends on the road, depends on the tire conditions. So anything other than the driver will be controlling the braking distance. Now he says which factors control the braking distance. Now you just have to make a decision over here. He says the speed of the car, tiredness of the driver, and then condition of the road. So speed of the car, right? So would it control this or not? Tiredness of the driver, again, this we don't need the tiredness of the driver. Condition of the road, yes, it is a part of the braking distance. And speed of the car, because it is except the driver, this is something that the driver is not doing. It's related to the vehicle itself. So yes, the speed of the car will also control this. So let's find out what option checks out these boxes. So ninth question is C, right? Okay. Question number 10, again from Hooke's law. Limit of proportionality, very straightforward. A point before the curve, that is going to be QQ. And then he says spring constant. So we have load, which is going to be Newton's extension is in centimeters. So spring constant is equal to F into Kx. So if you want to make K the substitute of the formula, this becomes F over X. So something Newtons per centimeter or Newtons per meter. So I can very clearly see that this is on the y-axis and this is on the x-axis, okay? So if I were to measure the gradient of the line PQ, I would most likely be calculating change in y divided by change in x. And on y-axis, I have the load, which is in newtons. On x-axis, we have extension, which is in centimeters, which matches the unit of the spring constant over here, which means that the line PQ, the gradient of the line PQ, will tell me this information about the spring constant. Okay, all right. Question number 11. First, he gives you the situation, and then he asks you what position or what introduction of new elements in this question will actually balance it. So first, let's calculate what is the anti-clockwise moment produced by the given situation. We understand that the formula for moment is F into D. So the force is 40 and the distance is 20. Now, one thing that I generally recommend my students is to convert this distance into meters. But since I can see that in all the options, this is the answer of the unit of the distance is in centimeters, I will not waste my time converting the unit because it's in all the options, it's in centimeters. So let's save time and not do so. And let's figure out the rest of the options. So what will be the moment because of this situation? So this will be F40 multiplied by 20. That is 800 Newton centimeters. Okay, so we want something equal to at least 800 Newton centimeters to balance this. Be that placed over here, be that placed over here, be that in any location, but its moment should be 800. Now first, let's figure out what moment is in each option. So it's 20 multiplied by 40, 20 multiplied by 40. This is 800. This is also 800, but this is 500. C and D are representing a value of 500 Newton centimeters. So I will not even consider them. So we have eliminated at least two options. Moving on to the correct answer. He says 20 newtons acting downwards, 40 centimeters to the right of the pivot. So we move towards the right side of the pivot. So we're going to apply a force at this location somewhere. 20 newton acting upwards, 40 centimeters to the right. So option B says that you have to move towards the right, but apply in this direction. Now notice that option B, if I were to use option B, that would mean that I would allow this rod to rotate in this direction. So it is going to follow the same direction as of the 40. So it will not introduce balancing effect, it would further unbalance it. So I need to make sure that I decide or choose the direction which makes sure that it counteracts or opposes this green direction or this anti-clockwise movement. So I should choose this option A so that it can move or provide movement in the clockwise direction, which will balance out or which will oppose this moment. So option A is the closest or the best answer. Question number 12 says, gives you a lot of variables. He says how much work is done by the worker. You see, it could have been two answers, but since one of them is not given, we have definitely, you can say we have the guarantee that we can choose one option of the other. So notice that P is also a force. W is also a force. Now, since we want to find the work done, that should be force into distance or force and distance in the same direction. So ideally, if everything is frictionless and the amount of work done is equal to the amount of energy gained by this object, then it could have been P multiplied by D, work into distance, force into distance, and weight, force multiplied by this distance, which is effectively gravitational potential energy as mgh, so that will be WH. As WH is not given in the answers, we have to choose option B, okay? All right, a battery is connected circuit, and again, this is from memory. Batteries, cells, petrol, diesel, fuel, coal, plastic, anything that combusts or anything that is chemical in nature has all its energy in terms of chemical potential energy, which you convert, or which that device converts into electrical for you. 14, which is the property of the both liquid and gases? So they fill their containers, yes, but for gases it generally takes time, and for liquid it's not necessarily going to be that way. Let's say if the glass is half full, but if in the same container you had gas would have completely filled it, no matter how far or how big the container is. So this looks good, but it's not entirely accurate. They are incompressible. No, gases can be compressed. They can flow. Yes, both can flow. They have particles in fixed position. No, this is entirely a statement for solid objects. So if I had to make a choice between A and C, A looks right, but in certain scenarios, this is going to get wrong. C is the best answer because that is always true in all circumstances, in all situations. Now, question 15 requires a bit of mathematical understanding, and you need to involve Boyle's law, which is P is equal to 1 over V, right? Okay, so, and of course, we have P1 V1 equals to P2 V2, or P1 V1 being equal to a constant value, because that is the underlying assumption, or you can say, at least for Boyle's law, if you're dealing with an inverse proportionality, that is pressure inversely proportional to volume, this is actually inversely proportional graph for mathematics. And if you take this over there, this becomes XY product is actually equal to some constant value. It will never change if they are truly inversely proportional. Okay, so what's happening in this question? He says, what is the possible explanation for this results? So what are you doing? Let's see. You increase the pressure, or you can say you've doubled it. The volume, if you increase the pressure by 2 times, then the volume should decrease by 2 times, which we can see very clearly is happening as it is. But we have to move forward as well. We have to check for other options. Is this true across the band? Now, when you decrease the pressure, or increase the pressure, sorry, by 3 times, the volume should have decreased by 3 times. Now, when you decrease this, or you can say 20 into 10 raised to power minus 5 divided by 3, the answer was supposed to be 6.66, but the answer is 6.0 something, which means that something is wrong. Is the pressure greater than expected or less than expected? It is less than expected, which means that something is wrong. Let's move on to the next option. I have increased the pressure 4 times, so the volume should decrease 4 times. So if I divide 20 raised to the power minus 5 divided by 4, my answer should be 5 into 10 raised to the power minus 5, but my answer is 4, less than expected. Now let's see what are the possible answers he's giving me. He says after pressure is doubled, the gas started leaking into the cylinder. No, it can get out, but it's not entering the cylinder. If it was entering the cylinder from the sides, then the pressure would increase because the number of particles would have increased. It would have increased the number of collisions, hence resulting in greater force. And of course, the conclusion would be greater pressure. The pressure, after the pressure is doubled, the gas starts leaking out. Yes, this seems like a plausible option because we are getting pressure less than expected. So something is happening. Particles are reducing. The temperature of the gas is constant. This is not an assumption. This is not the result of this question. This is actually an assumption while doing this experiment. The temperature of the gas is increasing. We can't guarantee this, and we can't see this happening over here. Whenever we are dealing with Boyle's law, at least, pressure inversely proportional to volume, we assume that temperature is constant as far as this question goes. So option C and D would have been wrong to begin with. For an intelligent student, he would have figured it out that C and D will not even be thought about. Okay, will not be even considered. So option B seems the right answer. Pressure is doubled or pressure is increased. It is leaking out. Question number 16, he says, in which options in the following question is thermal expansion useful? It's in your benefit. So do we use the thermometer by exploiting the thermal expansion of the liquid? Yes, so it's useful in P. Can we open lid containers by pouring hot water onto them? So the metal lid expands, loses its grip on the glass jar, and eventually is easier to open. So is it beneficial for us? Does it make our life easy? Yes, it does. But let's move to R. You see, we have metal beams and everything in place, right? But what if this were to expand in this direction, or this was to expand in this direction? In any direction, the most fatal direction in which the expansion would not be acceptable is actually in this direction, right? What if the roof starts expanding and they actually, you can say, budge out of that position entirely? So in R, we cannot afford expansion because everything is fitted into very tight tolerances, and even in construction we can't allow this expansion, at least. So it's not useful. We don't want this in R. We want this in P and Q, but we don't want this in R. So what is P and Q only? So B. 16's answer would be B. Question 17, and again from, I suspect, conduction, convection, radiation. Statement about copper explains why it's a better thermal conductor. So atomic vibrations, they are present, but yes, it causes it to move slowly. Okay, through copper, pass on kinetic energy. Yeah, we understand that these both statements are true, but does it explain why is it better than glass? The density, because these both process also happens in glass as well. In non-metals, particles also vibrate and transfer energy from one point to another. But what's special about copper? It's a metal. So the density changes, no. That is a convection current statement, and it's for solid, it's for liquids and gases. So D seems to be the right answer. Free electrons makes them faster, or makes them better at conduction. Question number 18, which statement describes the transfer of thermal energy in liquid by convection? Decrease in density, of course, convection is change of densities. Free electrons, no. That is for solids, specifically metals. Infrared radiation, that is electromagnetic radiation, and that is simple third part, infrared radiation. Particles of the liquid vibrate past, no, that is for solids. So A was the right answer. This is a part of the definition primarily. Which characteristic describes the image formed by plane mirror? Now this is a plane mirror, right? You're standing in front of it. What sort of image do you see inside the image, inside the plane mirror? So this is the image. This is the real object, right? Okay. So the image is real? No, it's virtual. Again, based on memory. It's upside down. Incorrect. It's upright. Yes. It's not real. It's not larger. It's virtual. It's not smaller. So the best answer is option B. Whatever you see on the outside is exactly copied on the inside. That's why a plane mirror is there. Okay, so this is a question about refractive index. Now let's make the normal first. This is the mistake that you do generally. We measure angle from normal, not from the surface boundary. This is the surface boundary. We don't use this for those measurements. We always use the normal for those measurements. Now, this is your angle of incidence, or you can say that this is our air or rare medium, and this is our glass, or you can say this is your dense medium, right? Okay. Now, this will be 35 minus 90, which will be 55. Yeah, that is 55. So this angle is 55 degrees, and this angle will be 30 degrees. So we draw the normal to measure angles. So let's figure out the refractive index. This is going to be sine of rare divided by sine of dense, or simply I divided by R, right? So this will be sine of 55 divided by sine of 30. When you calculate this, you're going to be 1.638 something, which is going to become 1.64. The 20 is C. Question number 21, he says, which of these examples, basically, if you go back to the book and if you refer to it, you will see that this is the exact diagram that they use to find critical angle, right? So any student who has an idea about this experiment would immediately figure out that this is not what we're looking for. This is not what we're looking for, although this is correct, but we are not looking for this. D is an impossible case. It never happens. C is where the critical angle lies. If you increase the angle a bit more than this, the light ray actually eventually comes out. So the angle of incidence, which sets the boundary, which is the last limit between refraction and total internal reflection, that angle in the dense medium is called the critical angle. So angle of incidence in the dense medium is only available in option C, which produces an angle of 90 degrees in the rare medium, right? And for the total internal reflection, there are two conditions. Is the light ray trying to move from dense to rare? And is the angle of incidence greater than the critical angle? So we can see that over here, the light ray is already in dense medium, it's in glass, and it's trying to exit into a rare medium. Only then you will see this phenomena taking place. Question number 22, measure the flaws in metal components, basically to detect the cracks in metal surface or metal sheets. So what sort of element do we need? Do we need an alpha emitter? Would that be a good option? You see, alpha is absorbed by atmospheric air. It is absorbed by a piece of paper. So if you were to detect problems in metal sheets, if this is the transmitter, let's say, and this is the receiver, How will you make sure that the alpha particles actually pass through the metal to see any change or to detect any change? So that's not possible. We can't use alpha because it's easily absorbed. So we made the decision that we need to use gamma radiation. Now let's make the second decision, that is about half-life. Can we afford 3 minutes of half-life? I understand that this is dangerous for human application, but the problem is that if you choose a 3 minutes half-life, the sample will decay so quickly that it will not be economically feasible for a factory to work with that. They will have to replace the gamma source radiation again and again. So instead, if we have a very weakly ionizing gamma radiation that has a half-life of 5 years, that seems like a much better economical decision than choosing a smaller half-life in terms of safety. So question number 22 is option B. Ultrasound is a type of, now he says only ultrasound. Now 20 hertz up to 20,000 hertz is what we can hear, is the audible frequency range. This is also a part of your memory, should be memorized by you. Anything above this is ultrasound. So 30 hertz falls in this category. We can't use this. He says only ultrasound. 300 falls in this category. We can't use this. 3000 hertz also falls in this category. We can't use this. So by elimination, we eventually land to option D, and we can see that this starts from 30,000 hertz and goes up to 30,000, still into 10 raised to power 3, which is a very high range. So option D was the answer. Question number 24, he says, what proves that a metal bar is permanent magnet? Now, for any element to prove its identity to be a magnet or being a magnet, it has to make sure that it repels from any end. You see, attraction can be done by any object. If let's say this is an unknown object and you bring in North Pole and it gets attracted, you bring in the South Pole, it gets attracted. Can we say this with can we definitely say that this is an iron rod or a steel rod or whatever this is? So attraction or being attracted is not the guarantee of this material being magnet itself. We can't say that this is magnet or not. If this was a magnet, for example, then it would have had poles, and from one end it would have repelled, and from the other end it would have attracted. So repulsion is the key for identity of a magnet. So this is again written straightforward in the book. He's just picking out these definitions. I'm surprised this is in Majon paper. He has given many questions in terms of definitions. Okay, so he says 4 labeled arrows. Which one is the right one? So if you know the magnetic field direction, you will see that from the North Pole, the magnetic field always points outward. So option A is incorrect. And if you see option C, so through North or through South Pole, it should be pointing inward. So option C is incorrect. What happens on the sides? The loop has to get completed. So when you complete this loop, the arrows are going to be like this. Is B in the same direction? No. When you complete this loop, like this one, it has to complete this loop, right? So D matches the direction. Question number 26, he says, a shoe becomes, now this is where static electricity becomes interesting. He will tell you which one is positive and which one is negative. Then you have to make a decision how that has happened. So there is a carpet and a person is walking on it, and while it is walking, the shoe gets a positive charge. This is what the situation has told me. So if the shoe has a positive charge, then what's the charge on the carpet? It's going to be a negative charge. So positive charges transferred, positive. This statement is wrong physics to begin with. Positive charges do not move at any cost. Only negative charges move. If they move from one object to the other, that will be remaining positive, and whatever object they go to is going to become negative. So negative electrons are transferred, yes. To the carpet, yes. The negative charges from the shoe have been transferred to the carpet, leaving a deficiency of electrons. So that's why the shoe becomes positively charged. And since now there is abundance of negative charge in comparison to before, the carpet experiences a net negative charge. So this is going to be transferred to the yes, it's going to be 26A. Question number 27. This is a bit confusing. The metal rod between positive and negative terminals of the battery, which show describe direction of movement of particles that flow in the conductor and their name. So we do have a conventional current that flows from positive to negative, and protons are generally, but again, protons don't move. Positive charges don't move at all. So what's the truth? The truth is that the charges will move from negative to positive. Option A and B were incorrect entirely. And what charges are moving from negative? Positive protons don't move. So electrons move from negative to positive. A negative terminal is a high density terminal because the electrons are abundant. They move through the circuit, go to the positive terminal because they are deficient on the positive terminal. There's a deficiency over there. Question number 28. Three identical cells connected in parallel to the resistor. Again, this is a very straightforward question, exactly picked from the book. What's the advantage of connecting cells in parallel? It is so that they last longer. That is going to be option C. Cell produce more energy? No. Cell supply more charge? No. The EMF is greater. That is when you connect the cells in series like this. Cells are connected in series, but over here the cells are connected like this. They're connected in parallel to whatever circuit there may be. Like there could be a bulb, there could be a heater. So what's the benefit? Why does it last longer? You see, first, previously, one cell had to provide whatever energy requirement of the cell of the bulb or the heater or the appliance was going to be. But now it is being shared by three cells. So the requirement actually reduces by 3 times. Now, when you reduce the requirement of charge, simple I equals to Q by T. If you want less charge, then if it's most definitely going to increase the time, right? It's going to last longer because you're requiring less energy. Anyways, moving on to the next part. A student has 315 ohm resistor. He says, what's the best combination, minimum or maximum? So minimum would be possible when you connect them in parallel combination, and maximum is when you connect them in series combination. So 5, 5, and 5, 15, sorry, 15, 15, 15 will be 45 ohms. So maximum is 45, 45, but you have to make a decision between 5 and 15. You see, if you connect them 15 ohm resistors like this, you'll have to use 1 over 15 plus 1 over 15 plus 1 over 15 equals to 1 over R. But there is a shortcut. I've explained this in classrooms as well, that if you have exactly the same resistor in any configuration, so 15, 15, 15, they're connected 3 times. So simply divide 15 with 3. If they were connected 4, exactly, so this will be 15 divided by 4. If they were, let's say, 5, 15 divided by 5, and so on and so forth. How many number of times they are connected, that will be used to divide the single value of the resistor. It will give you the answer for the parallel resistance, and you won't have to do this to save time. So this is going to be 15 divided by 3, which becomes 5. So very straightforward. Question number 29 would be B. And you can use these techniques in P2 questions as well. Question number 30, he says that the value of R is increasing. Now notice that these are just voltmeters. They are not doing anything to the circuit. They are just there to measure the voltage. Do we need to worry about this? No. So if I remove them from the circuit so that the circuit looks a bit simpler, so now it makes a bit more sense. It gets easier to look at least, right? So let's see. So if the value of R is increasing, what's happening to the overall combination? You see, the overall combination, let's label this R1, let's label this R2. So I want to find out the trend of this system. So what's happening? So 1 over R2 plus 1 over this R variable, let's call this Rx, equals to 1 over RT, the total resistance. If you take the LCM and you figure out, then this is going to minimize as R2 multiplied by Rx divided by R2 plus Rx. So primarily another shortcut, product over sum for parallel resistors. So if you increase the value of R, the value of RT increases. So the whole combination experiences a rising resistance if you increase the resistance of one of the components, right? So if the resistance increases, this one and this one are connected in series. What's going to happen to the voltage? If the resistance of this part is increasing and the resistance of this part is even not changing, larger voltage will show up over there, and smaller portion of the voltage will be available for R1. So what's going to happen to the voltmeters that were connected over here? They're going to report the same changes as we're discussing right now. So V1 will experience a smaller voltage or a reducing voltage, and V2 will experience an increasing trend. So what's happening to V2? V2 increases and V1 decreases. So question number 30 is part B. 31, the power consumption. Again, this is for electricity energy consumption prices. So power consumption is 1500, cost is 24 for 1 kilowatts of energy. What's the requirement for 10 minutes? So we have to convert this into kilowatts. So 1500 watts divided by 1000, that's a general formula, multiplied by 10 minutes, which is this one. So minutes have to be converted into hours, so 10 divided by 60. So in this part, we're converting this watts into kilowatts. In this part, we're converting any time into hours. It could have been days, it could have been weeks. We will convert this into simple hours. Multiply this with the cost of 1 kilowatts of energy. So that is going to be 24 cents per kilowatt hour. So you're going to come out as 6 cents as your answer. This is option A. Question number 32, he says, which one of the options does not affect the induced EMF? You see, this is from the topic of Faraday's law. So if you want to increase the induced EMF, you can increase the speed of the movement of the magnet, you can increase the speed of the coil, you can increase the number of coils. If you do these things, the induced EMF increases. That's why we make generators with a lot of coils and very large in size, so that more magnetic field can cut, more voltage can be generated, and consequently more energy as well for the same motion. So what does not affect? Number of turns. Of course, if I increase the number of turns, it will increase the cutting of the magnetic field, increasing EMF. So yes, it will change that. Changing the height h from which the coil is being thrown. You see, if I increase the height of the coil, its speed will increase. And if the speed of cutting of magnetic field increases, I'm effectively changing the rate of magnetic field being cut. So a higher induced EMF will be experienced. Changing the direction of the North Pole. Okay, so this looks fishy, but changing the strength of magnetic field. Now, if I use a stronger magnet, it will increase the magnetic field cutting and increase the induced EMF as well. So the option closely resembling this is option C. This will not change it. Even if you put in a south pole or if you put in a north pole, it does not change. Of course, it will change the direction of the current in the coil, but that's not the question. The question is about the magnitude. Okay, the magnitude will not change. All right. 33. Alpha scattering experiment. What evidence did it provide? Again, a question directly from the book, from a part of memory. So nuclear fusion, no, that didn't help us do that. Radioactive decay, nope, that was discovered in terms of GM tube, alpha, beta, and gamma. The existence of isotopes, no, that's a chemical discovery. So alpha scattering, yes, this is the main discovery of science, because we were baffled by this idea that how is it possible that there is a sheet of paper in front of this, or a sheet of gold nucleus, and the alpha particles can pass straight through. 99% of them can pass straight through. What's with this? What's happening? Why are they not being stopped? And some of them are actually coming back, and very few percentage are actually going off course with angles less than 45 to 90 degrees, between 45 and 90. What's happening? So this experiment of alpha scattering actually gave us the idea of the modern nucleus, what it looks like today. So this is what 33 was about. 34, represented by the symbol, again, basic chemistry. We can see that the number 27 represents the number of protons, and 59 represents the number of protons plus neutrons. So if you want to find neutrons, you have to subtract them. So 59 minus 27 would have been 32. So option A is the answer, right? Okay. And if you see in chemistry, this is the representation. So A, Z of the component X. So this number represents protons and protons and electrons. This represents protons plus neutrons. 35, he says 79 protons, 118 neutrons in a nucleus. A neutral atom means that same number of protons and same number of electrons, so that there is an overall zero charge. So 79 particles are positive, so 79 particles should be negative, so that overall it becomes neutral. 36. This is a good question in terms of memory, at least, and logic. So he says that the background radiation is being subtracted, so the corrected count rates are written. So you don't have to worry about the background radiation. And different materials are inserted one at a time. So it's not like this that the one you remember or memorize from the book is that we have a lead sheet, piece of paper, then aluminium sheet, then lead sheet. This is paper, this is aluminium sheet, and this is lead sheet. And you introduce alpha, you introduce beta, and then you introduce gamma, and then you memorize this diagram. So you have to develop a logic from this diagram and use it for this question. So when there is no sheet, that means that the general reading, when there is nothing between the source and the detector, there is a reading of 450. And when you place a thin piece of paper, the reading is not changing, although the reading has increased a bit. So both situations would have been confusing for the student. Why is it increasing? And what if it had decreased to 440? Would that still count as alpha being present? No. Because when we go to the radioactivity chapter, we realize that the radioactive decay is random in nature. Now, randomness means the readings fluctuate a lot. Unless or until there is a drastic change or a meaningful change observed in the values, we are not going to consider them presence, or we're not going to consider them as evidence for the presence of a particle. Okay, so we have and background radiation generally accounts for a value of 20 to 30. So this value is not even close to that. Although he mentions that the background radiation is accounted for, but for the sake of argument, even if it wasn't, it's not even changing that, right? So even if it had increased or even if it had decreased slightly, it does not give me the idea, does not give me the right or the maximum guarantee that alpha is present. So at least in my answers, alpha should be absent. So I'm left with C and D. Okay. Now he says thin aluminium sheet. Now, aluminium sheet disturbs beta particles and lead sheet disturbs gamma particles. Is it decreasing the value drastically? Yes, it is. And is it changing from 450 to 285 because of the lead sheet? Now notice one thing. Lead not only stops or reduces gamma radiation, it also stops beta radiation. So lead is good at absorbing everything. So when you observe that the readings are decreasing even more than beta, that is accurate. You see, lead sheet will absorb beta as much as aluminium did, and further will absorb gamma radiations as well. Okay, so we have the absolute guarantee that yes, beta was present and gamma was present. Beta presence was guaranteed by reduction due to the aluminium sheet, and gamma reduction was guaranteed by lead sheet. But is there alpha present? No, alpha is not present because piece of paper did nothing. Now, why has this value not decreased to at least up to a zero value, or at least close to a background radiation value? Because gamma radiations only get absorbed, they can't be eliminated completely. That's the problem with the gamma radiation. But anyways, you can research that online as well. So 36 is C. We can only use lead to decrease their intensity, but we can't finish them completely. In fission reactant, which particle? Yes. So we don't introduce alpha, we don't introduce gamma, we don't introduce a proton, we introduce a neutron. Why? Because neutrons are neutral. We are trying to split this atom, but if we had brought in a positively charged proton, there would be so much repulsion between them that won't even be absorbed, won't even make a difference. So we had to choose a particle that was neutral, so that was at least allowed to come close to the nucleus, which is strongly positively charged. As the nucleus gets absorbed, this becomes unstable and then splits. This is nuclear fission reaction that we use in nuclear power plants. What is the purpose of the moderators? Now, you have to remember this, you have to memorize this. Moderators' only job is to slow down neutrons and bring their energy to such a level that they can be at least captured by the uranium atom. If they're too energetic, chances are that it won't have enough time to actually enter or actually create an unbalance in the uranium nucleus. So we have to reduce their energy the moment they get released out of the uranium nucleus. So moderators are there to slow down the neutrons. But there is one more thing that actually absorbs these neutrons to stop the reaction, and they are called the control rods. Control rods are responsible for absorbing them entirely. They will be absorbed, and this is how the nuclear power plants are actually stopped. Or, of course, under this emergency situation, they use control rods to stop the reaction entirely, because otherwise it will become a nuclear explosion like Chernobyl. In which region of electromagnetic spectrum does sun? So sun is emitting three spectrums primarily. So this is infrared radiation, there is visible light, and there is ultraviolet. Ultraviolet is what fights with the ozone. Visible light is what we use to see objects around us, and infrared is what causes its heating effect. You see, when you go into the sun, visible light is not causing the heating effect. Ultraviolet is not causing the heat effect. Infrared radiation is what causes the heat that you feel when you're standing in the sun. So it emits its radiation, or highest energy spectrum is in infrared radiation. Microwave does not come, radio does not come, X-ray is not a part of the sun's radiation spectrum. 40 again is apart from memory. You can pause the video, read these sequence of events, and just memorize them as it is. This is a birth of a star, and eventually when it becomes a star, right? So it says until it becomes a red giant. So first we start with X. Yes, the gravity causes the gas to implode. It implodes onto itself. Then we have no expansion does not happen. Inward forces of gravity balanced by the outward forces. Yes. So first it should be X. Second should be W. Then what happens after that? So Z, most of the hydrogen has converted into helium. Yes, that is when its life cycle is ending or is close to its end. So when it becomes a red giant, this is what actually happens. hydrogen is running out very quickly, and helium is most probably helium is a higher concentration. So Z should be the next stage. So this is 3, and the last stage naturally becomes stage 4, which it expands and become very large in size as opposed to the original size of the star, because helium is decreasing, right? Hydrogen is decreasing, and there is a very concentrated core at the center, but the rest of the gas escapes because of poor gravitational attraction, right? So this is going to be option D.